you and got it, and come over here and scroll down. Okay, so yes, welcome everybody to our last week of new material for the big data class. And probably today will be actually our last day of new material for things that we're going over before the final exam. We'll cover all the material today, and then Thursday we'll go over a little bit more about what to expect from the final exam and just review how to prepare. And then those of you who are graduating this year, that will be your last in-class session, and you'll have your in-person exams one-on-one with me next week. And then the non-graduating students, next week we'll talk about your final project and how that will be built into the final exams for you all. A couple of announcements here before we get into the last little bit of material today. So the first announcement here is your last lab, the one that was on Friday. Most labs, there are lots of good grades. The last lab, though, had a lot of poor grades in it. And I guess the main cause of this is that a lot of students submitted a combination of an index and a query that did not speed up. The query might have been correct, but the index did not speed up that query. And if you're in that situation, then I gave you 0 out of 4 points for the lab for that error. And I guess I'll also remind you that you probably didn't use the explain command just to verify that your queries were actually using that index. The 0 out of 4 points, not a huge deal in the grand scheme of things, but if you come into the final exam and make those same sort of mistakes, then you will get very, very few points on the final exam. So definitely make sure that you understand why you did not do well on the lab if you did not do well before coming to the final exam. My solution, again, use this combination of the reverse, lower, like, and text pattern ops in order to do the query. We'll talk a little bit more about that later on today in class. Our last topic for today is this idea of full text search, so how to efficiently search through large document collections. And we'll talk about some of the situations where this works and some of it doesn't. Last thing to say about the lab, though, if you did use this PG trigram operation plus the GIN index, or the PG trigram extension plus the index, you got full credit because it wasn't what I was intending, but you did answer the literal question that I asked. And so I always give full credit for correct answers of what I literally asked, even if it's not what I intended to ask. You should know, though, that the solution that you provided is actually much, much slower than the B-tree solution based on this up here. And my guess is that most of you who provided this solution have actually no idea what this solution is doing, and you just copied and pasted something from ChatGPT, which, again, according to the policy in the class, totally okay. But you should know that if you did this, it's probably, I don't know, somewhere between 5-ish students who did this. Expect me to ask you how that works on the final exam when we're doing our one-on-one talk about things. So you got the full credit for the lab, but you will have to talk to me about how it works at some point. More announcements. So no lab this week. The data science capstone presentations are going on, so I won't be available for the lab. There is a simple assignment, though. I think most people will find it pretty fun. I posted it on the GitHub issues here. I don't know, maybe fun's not the right word, but all you have to do is you watch some videos, and these videos are like so here's the senior chief technical officer at Instagram talking about how they use Postgres inside of the Instagram infrastructure. Reddit also uses Postgres in its backend. You can see some Reddit engineers talking about that. Pandora, if you use that service, they use Postgres. There's just a handful of videos here to watch. There's a lot listed here. You're only required, so the assignment's out of 2 points. If you watch 2 videos, you get the full credit. So that's roughly the equivalent of the lab time. But if you would like more extra credit, you can watch more videos and get more extra credits. And this will be the last extra credit opportunity of the semester. There's still a handful of other sort of outstanding extra credit opportunities that you can still submit to me and get, but I won't be posting any new ones after this. I think it's cool to see like actual engineers doing cool engineer things and not academic stuff, talking about how the stuff you've learned in class is actually useful in the real world. So I think this is one of the more interesting assignments, and it should be like low stress, easy to do. Expect everybody to get lots of points on this. The next announcement, there are a lot of good GitHub issues being posted. I think everything's been resolved. I haven't responded to a lot of things because I think it's all been resolved either in the question or in office hours, but if not, then let me know. And again, today we're going to finish going over the new material. Thursday, final review session, go over the exact format, everything, what to expect from the final. And very last announcement here, the non-graduating students, you can now sign up for your final exam time slots on this link if you would like. And no other announcements. Any questions about anything administrative? Yes. For the videos over here, how do you prove that you watched the video? You just reply to this issue. I think I asked just 3 facts that you learned per video. And again, I don't think I mentioned this either, the due date. You just, anytime before you have completed the final exam with me is fine. So you have a lot of time to complete these, watch these, whenever's convenient for you. Good question. Any other questions? Administrative, yes.
What's going to be, what are we doing the last week? Like, what are we doing next week for class?
So non-graduating students, next week, we will still have class next week. I'll basically just explain what you need to do for the final project and give you all time to work on the final project. There's no like new material for the final project. It's just combining a lot of stuff together to build your own database. Last chance, administrative questions? Okay. Today then, our last technical topic for the semester, our last new material. We're going to be talking about new types of indexes. Last week we talked about the B tree, a lot of time about the B tree, and we also talked about all of these different like scanning methods and joining methods and the aggregation methods, sorting. All of those things are still applicable for every type of index in Postgres. But now we're going to think about them not in terms of the B tree, but in terms of other indexes. And originally, I was planning on that we would be covering all of the different types of indexes in Postgres, but I've crossed off most of these, so you don't have to think about them, and only the GIN and the RUM index are the things that you'll have to know for the homework and the final exam, the GIN and the RUM index. And so that is what we will go over today. It seems like, I don't know, people are extra busy with graduating and things, so figured we can cut down to just the minimum amount that we absolutely have to know. Again, for your homework assignment, so the indexes homework assignment, you'll have to use the GIN in the RUM indexes to speed up some of those queries. Those queries are doing things called full text search or searching through the JSONB entries. And so today in class, we're going to go over high level what this means, full text search, and then we'll go into the details on how these indexes speed up those operations. And after today, you should be able to do everything for the homework assignment. And besides just the homework assignment, you should know everything for all of these like PDF packets, the final practice problems 2 or 1 that I've passed out so far. Okay, so we'll start off sort of motivating this idea of full text search by talking about some of the difficulties with full text search. And so we've seen queries that look something like this. We should know what it's doing, that if we're selecting something from some table where some text column is like some expression, and we have these percent signs, in this case on both sides of this word corona here, that this should find any tweet that has the word corona anywhere inside of that tweet. And it doesn't even have to be just like the word corona, coronavirus would also match this, the anywhere, any tweet that contains this text anywhere inside of it will match it. And it turns out that B trees cannot speed up a query like this. In your lab, you saw that B trees can speed up a query like this, where the percent sign is only on one side of the like operator, so something like corona and then percent. And the reason that it can speed up things like this is because that this is essentially equivalent to a less than operation combined with a greater than or equal to operation. And we've talked about how the B trees can speed up these sort of range queries, because all of these, any text value that sits between corona and corona B is going to be sequentially stored in memory or on the hard disk and using the B tree. And so the B tree is able to speed up operations like this with the percent only at the end. One of the things we did in the lab is, what if we sort of reverse that? So where in this query up here, the word corona comes at the beginning of the phrase. What if we wanted corona to be at the end of the phrase, something like this? And this is where a lot of people made mistakes in the lab and didn't get credit. That it is possible to speed up something like this, but you must be very careful, because you can't just speed up a query like this. This query right here cannot be sped up with a B tree, but an equivalent query can be sped up with a B tree, where you reverse the text and then reverse your string like this, so that the percent sign gets placed at the end, and then you can speed it up. For a B tree, you can only speed things up if there is 1% sign at the very end on the right-hand side of your expression like this. Another thing that I talked to a handful of people about in the lab, but we didn't actually, the lab didn't go over it in detail, is the performance difference of the like and the I like operators. How does that affect our performance with a B tree? And the answer is that if you use the I like, then you get actually really bad performance. And so this will be something that's important to understand for your final exam about why do you get bad performance if you use the I like operator instead of the like operator. And the answer is because of again, the I like is case insensitive. And so in order to do a case insensitive search on something like this, you have to expand this to many, many expressions, where the greater than or equals to and the less than now include many combinations of greater than and less than with uppercases and lowercases in different spots. So this first condition up here, all lowercase. This next condition down here has some uppercase letters at the beginning, and everything else is lowercase. And now the uppercase has moved to the O. Find everything between those. And it turns out that there's going to be a quadratic number of different combinations of uppercase and lowercase letters here. And so that's a lot of different queries that you have to try. And so the I like, in the worst case, is going to be quadratically more slow than the like operator. So in general, if you're thinking you want to do an I like operator and you're trying to speed it up, that's in the lab, why my solution uses that lower function to make everything lowercase and then use the like operator instead. But that will make things faster. An important sort of aside right here is that we've talked about in SQLite how SQLite does not obey the SQL standard of the like operator being case sensitive. In SQLite, the like operator is case insensitive. And a consequence of that is that the like operator in SQLite is just always going to be slow, or it's always going to be slower than it would be in Postgres. There's no way to avoid this sort of quadratic penalty in SQLite. And one of the reasons why Postgres maintains this distinction between like and iLike is to prevent situations like this, where you get that penalty from the case-insensitive search. So I guess the takeaway from all this is that if you have this sort of like one-sided wildcard query, that's not going to be super useful for full text search. There's no way with just a B tree to find a word anywhere in the middle of a query. You can only find it at the beginning or at the end of the query. And full text search, we're going to try to find, like, our motivation is how do we find words that are somehow in the middle of our text somewhere. Any questions so far? Okay. I want to very quickly talk about this full text search. I'm abbreviating it FTS, common abbreviation for it, outside of Postgres. Just do a minute or two on this. This will give us some like background motivation for the Postgres specific stuff. But this background stuff, there's a handful of links here if you're interested in it, but not something required for the final exam to know in detail. The main thing about full text search is that it is a hard and unsolved problem. Actually, that if you are all graduate students, then in order to like fully study full text search, this would be like multiple graduate level classes of different things going on. So we're not going into anywhere remotely near the like state-of-the-art details of full text search. We're just sort of scratching the surface here with this lecture today. Yeah, even like Google, Bing, famously not very good in many situations about full text search. And so we're not going to beat them just today. Important thing here, there is no SQL standard for full text search. So every relational database, whether Postgres, SQLite, MySQL, does something totally different for full text search. And most systems that are like full text search specific things designed to be good at text search, do not use SQL at all. So we call them, again, the NoSQL databases. This is a different type of NoSQL database. The last sort of type we've talked about, I've mentioned MongoDB a lot. They emphasize the lack of ACID transactions for speed. This type of NoSQL database emphasizing just the ability to do full text search. Some popular ones here, Elasticsearch. It's the most popular one. But again, not SQL syntax, so kind of like its own standalone thing, hard to remember, hard to use, hard to set up. It's more complicated than Postgres getting it set up, getting whatever your port situations or whatever you need set up with Docker Compose. Let's see, I'll skip over those things, just highlight a couple of other common solutions, Lucene, Solar, Grunga, other popular full text search systems. The main advantage of doing it inside of Postgres, doing full text search inside of Postgres, is that you have like your full SQL capabilities. For example, you're able to do joins on things with full text search. And the full text search in Postgres, it's not quite as advanced as some of these other full text search systems, but it's generally considered much, much better than all of the other sort of like relational databases full text search. So things like MySQL, SQL Server, even Oracle, the really expensive one, millions of dollars per license. Postgres full text search, widely considered much better than all of these. Okay, and I'll skip down here we'll start talking about the stuff that you actually need now for your homework assignment and for understanding what's going to go on in the final exam. I'm going to start here in this full text search in Postgres section. We'll talk about the syntax of how to make full text search happen. And then after we talk about that, we will switch over to talking about these JSON and RUM indexes and how they make full text search faster. So in Postgres, there's two important data types that you'll need to be familiar with. The first one here is the TS vector. TS stands for text search, and vector is like a vector from math. So there's a text search vector. And there is a function here, toTS vector, which converts whatever string is that you're trying to do a search on into this TS vector type. So here, this takes two parameters, TS vector, toTS vector. The rightmost parameter is the thing that you are searching, the text that you want to search. And this leftmost parameter is a language that you're doing the search on. The simple language does no language-specific special things. And so inside of the TS vector type, this is sort of the contents of the TS vector listed down here. The thing inside of the string right here, these are the individual words that have been extracted, the individual words right here that have been extracted, and the number over here is the location in the string that that word was located at. So this document over here on the right-hand side, this is a testing example. The word this, the one right here, and then is the two right here, and so on. And there's no special language-specific processing. You won't need to necessarily, so for example, for the final exam, I'm not going to ask you anything about the details of how this is formatted, this representation of the TS vector. But as you're reading through the documentation on the JSON and the RUM indexes, they will be just displaying this information a lot. And so it's useful to understand what this is representing. In general, in most cases, you won't use this simple language right here that does no language processing, and instead you'll specify what language you want to do the processing with. And this function right here will perform two types of linguistic operations. The first one is called stemming, and in stemming you convert all of these words into somehow what the root word for that word is. So if we have these three examples right here of words that could be in your document, example, examples, pluri, exemplary, all three of these words somehow come from the same root word, and so they'll all be converted into this EXAMPL word in the TS query, or sorry, in the TS vector right here. This isn't a real word, but that's just how Postgres is going to store it internally, so that if you search for exemplary, it'll also find example. The second modification it will do to your data is called stop word removal, and this will remove short non-semantic words. So things like this is a, you're not normally searching for these sorts of non-semantic words in a document, and so it'll remove those from your document. And so down here is an example of, we have this toTS vector using the English language right here. This is an example, and this is the actual contents of what is stored in that TS vector. So the word example over here, truncated to just example without the E at the end, and the word testing over here converted to the word test over here. Any questions about this TS vector? What's going on? Nico? Question is, how does it know, or how does it recognize the language? There's two parts of that. The first part is that you'll have to specify manually what language you want to use right here. There's no way for Postgres to automatically determine the language for you. Postgres has about 30 or so different languages built in, and they all have different features to them. So for example, here this is English, and these are all these stop words that get removed are specific to English. And if you were to change this from English right here to a different language like Chinese, then these words right here would not be removed for English. So for each language, there is a special just dictionary of words that are going to get removed. There's also a special stemming library built in that has a very complicated set of rules that it goes through. Again, language specific. So like in English, one of those rules is that if a word ends in ing, then you can get rid of that, and the thing on the right or the thing on the left is like the root of the word, and that's the thing that gets stored. So here for testing, removing ing and keeping only test, that's an English specific thing. English is actually very, very easy relatively to do all these operations with. Other languages, so like Spanish, an individual verb in Spanish has 212 different forms they can be in. So the rules are much more complicated. Languages like a lot of Asian languages, Chinese, Japanese, Korean, they don't actually even have spaces between their words. And so even deciding like what a word is a hard computational problem. And so if you use those languages, Postgres has its own set of rules for determining what is a word and what is not a word. So a lot of complicated things going in here. For our purposes, or the reason we have these complicated things is because they'll make your text search more accurate somehow, getting you the right documents, whatever you're looking for. But we're not focusing on this accuracy bit. We're going to be focusing in this class just on how Postgres is making things faster. And so you need to know that it does these things, but you don't need to know the details about how or why it does these things. Good question. So that's the TS vector. The TS vector, this is storing the actual data that is in the database in a form that is possible for text search. And then the TS query is how you represent the actual search itself. And so there's, again, a toTS query function. You specify the language as the first argument, and then there's a complicated sort of syntax available about what the query looks like. So in this case, if I'm searching for all of these different words, the query must have this and the word is and the word and example and test. In this case, the stop word removal removes all these words over here, and we're only searching for the word example and the word test, only searching for these two words right here. And there's, again, a complicated syntax on how you can combine things together. So you can use the and operators, the or operators, and there's even a lot of other operators built into the syntax here, but these are the sort of two most obvious about what they do. Combining it all together, you get a query that looks something like this. So select text from tweets, where toTS vector. Again, the thing on the left-hand side, the toTS vector, this is the text inside of the tweets here that we are searching, text inside of the tweets. This is the document that we are searching inside of. And the toTS query, this is the thing that we are looking for. So usually the toTS vector function is going to have the column inside of it that comes from the table. So here the tweets database has the text column, or the tweets table has the text column inside of it. That text column being passed to the toTS vector function. And the toTS query usually has no columns from the table anywhere inside of it. That the language over here hard-coded and the search term over here hard-coded or provided from like a user form on a website somehow. The only thing in here that is coming from the actual table is this text value right here. And so what we're going to be spending a lot of time today talking about is how this @ operator gets sped up inside of Postgres. Maybe before I do that really quick, I'm going to jump over to our homework assignment, this Twitter Postgres indexes, and we'll just take a look at where this is coming up inside of this assignment and to get a high-level idea of why you need to know what we're talking about next. So again, I'm looking at your last final homework assignment right here, and I'm going to go to this SQL normalized batch folder right here. This folder, again, contains 5 queries inside of it. And one of your jobs in this homework assignment is to write indexes that will speed up these 5 queries. This last right here, this last query right here, you can see is a very complicated query, has a lot of different things going on, select distinct, there's a join going on, there's this grouping by and ordering by. So as you're thinking about how to speed up this query, you'll have to think about all of those different types of internal algorithms that Postgres uses to implement these queries and how to speed those up. We talked about those again last week, but here what we're focusing on right now is line 13. Inside of this where clause, there's this 2TS vector, English text, and 2TS query coronavirus right here. So this line right here in particular is the thing that we will have to speed up for using this, new type of index called a GIN index. All of the other things inside of this query can potentially be sped up with a B tree index, but line 13 right here, this will need a GIN index in order to speed it up. So we'll talk again about how this GIN index works, and that will help you implement the solution for this problem. Any questions so far before we move on to how the GIN index works? Okay, I'm going to go over now to this our haber.com webpage. This blog post that is serving as our textbook for this portion of the course. Again, I'm going to go over at a high level some of these figures to get you the intuition, point out some of the things that you need to know about this index. But you're still responsible for reading this whole document, and I could potentially ask you on the final exam, for example, anything that comes from this document right here. And this document that we're currently looking at is the explanation of the GIN index. So this first picture right here, this is sort of the most important one to understand. Let me zoom out just a little bit. This is the most important of the pictures to understand. And in order to understand the picture, I'm going to scroll up just a little bit and to talk about these sets of SQL commands right up here. The picture down below is a picture of what is happening inside of these 4 commands up here. So this first command is just creating a table for us. The table has 2 columns, the actual documents that we'll be searching over, and it has this additional column here, which is the TS vector, which is again going to be this searchable representation of this document over here. And then they're inserting everything into the text column, the document column right here. This is the actual documents that we will be searching through. Notice that in this insert over here, they're not inserting anything into this TS vector column. They're only inserting things into the document column. We know they're only inserting things into the document column because in this list of columns right here, it only contains document and it does not contain TS vector. There's a common pattern for how things get inserted. For your homework assignment, you don't need to know about this pattern because all the insert stuff is happening in the Python code and it's already taken care of. But as you're reading through the documentation, just to understand what's going on, understanding that they're doing this pattern of inserting these 2 columns separately. That they start by inserting the documents right here, and then they update the table, setting the TSV column over here, set doc TSV to be equal to 2TS vector of doc like this. So they're doing it in sort of a 2-step process in their tutorial here. Everywhere where they do this, they'll do it in 2 separate steps, but you don't need to, I guess, implement that yourself. The important thing that you'll have to implement is the actual create index command down here. And so after they've done this, they're creating the index on the TS vector itself, not on the text. And this picture down here will show us what that TS vector, what that GIN index looks like. So the GIN index, what it stands for is a generalized inverted index. Is a very common data structure. It's sort of a modification of the B tree. And this top section over here is a B tree exactly as we have seen it in the past. That each one of these boxes over here is a page inside of Postgres. And again, each one of these like circly boxes inside of the page that are in white, these are the column information that is being stored inside of that page. In this case, though, this column information does not come directly from the column that's provided. That when we were using a B tree, the whatever column we provided right here that was we were creating the B tree on, that value literally gets copied into these circle boxes. For the GIN index, though, the GIN index goes inside of this data type over here, whatever this data type is, and splits it up into parts. And in this case, the TS vector, the way that it gets split up into parts is that each word of the data set gets its own part. They don't actually show in this part yet exactly what the TS vector looks like. But if we come back over here, take a look at the output of what a TS vector looks like. It's each one of these things that's down here. Each one of these things that's down here, these are the contents of those circle white boxes. So in your TS vector, whatever the contents are down here, this is the stuff that's inside of those circle white boxes. And so again, if you're using the English processing, you'll have a smaller amount of things in the circle white boxes than if you use the simple language processing, which does not do any processing, and so you have more things, more words in the TS vector, more items in those circle white boxes over here. So these, again, circle white boxes, these come from the TS vector. These black boxes are things that were not explicitly drawn in any of our previous drawings of the B tree, and these black boxes represent the tuple IDs of any matching row that contains whatever this word is up here. So in this case, if we look at the word good, there's only going to be one row in the data set that contains the word good, and it will be stored at position 1, 2. If we look back up here at this data set, I'll do a Control F right now looking for the word good. We can see that there is in fact only one word, only one line over here that contains the word good, and it is this one right here. We know that this row right here happens to be stored at position 1, 2 because that's what this tuple ID is down here. If we're doing a search for the word good in our full text search system, we want to find all the documents that contain the word good. Then we traverse this B tree the same way we've traversed the previous B trees, looking for the word good. We find it, and we see there's only one tuple ID right here. So only one line contains the word good. A more complicated example is this word sit over here, where there's now 2 tuple IDs instead of just 1 tuple ID. In the standard B tree, there's always exactly 1 tuple ID for each one of these white boxes in the leaves, but in the GIN index, there are going to be many of these tuple IDs per word up here. So if we see the word sit over here, if we're, for example, searching for the word sit, we'll do a Control F up here, S-I-T, and we can see that there are, in fact, two rows up here that contains the word sit. This one literally contains the word sit. This one contains the word sits, plural, but after the stemming operation, the plural S over here is removed. We get the root word of sit, and only the root word sit is stored inside of our GIN index because only the root word sit is stored inside of our TS vector. And so that's why both of these 2 lines over here match to the word sit. This, if there is a small number of tuple IDs that match whatever the word is, then those tuple IDs will be stored directly inside of the page that contains the word itself. So these black boxes over here, these are called a posting list. So this posting list right here, it's circling, in this case, the right side over here contains only one black box, only one tuple ID in the posting list. But anytime when these black boxes, anytime when these tuple IDs are stored inside of the same page as the search term, we call that a posting list. And that only happens if there is a small number of tuples, small number of rows that match whatever that search term is. In this case, 1 or 2. If there are many, many rows that, or many, many tuples that match whatever our search term is, then Postgres will store those inside of a separate page called a posting tree. And in the posting tree is actually multiple pages, another B tree structure, that these tuple IDs are stored inside of a B tree structure. And so here, this word slit over here, if we come down here, we can see that this word slit matches many, many tuple IDs down here, and too many to fit inside of this page over here, so Postgres has put it inside of its own posting tree down here. And again, the posting tree is its own separate B tree structure. I'll just, so we're looking at this word slit, has many, many tuple IDs down here. Come back up here, do a control F for the term slit, and you can see that there are, in fact, many rows that match this word slit. It comes in many forms inside of here: slitter, slit, slits, slitted, and all of those are getting stemmed together into just this one word slit, and every one of these rows is matching, and so every one of these rows has a corresponding tuple ID. It's a lot of rows, so it's again stored in a posting tree outside of the main page, outside of the main B tree index. We'll talk here in a second about why we have this structure about the posting lists versus the posting trees, but are there any questions just first about what the structure is? Yes. Yes, thank you. So the question is, previously I said that slit and slitter were getting stemmed into the same word, but Alex pointed out that over here in this square box over here in this leaf of our B tree for the GIN index, we actually have both words separately listed, slit and slitter listed. And so the stemming operation in this case considered slitter to be a different word than slit. And so those two things are listed differently. So that's a good observation. All of the tuple IDs are going to have the word slit somehow without slitter. So here, slits plural. I think slitted, the past tense, will still get trimmed, stemmed down to the word slit. But they do not all have the word slitter. So this row here has slitter. This one does not have slitter. And so this one will be contained inside of this posting tree down here, whereas they will all be contained inside of this posting tree over here. So this posting tree is smaller than this one because slitter appears less in our data set than just slit by itself. So yeah, good point. So here we have slitted. Question is, which one of these, where is this row going? Is it going into slitter or into slit? The answer is a two-part answer. The first part is for the purposes of, say, the final exam or even the homework problems, you're not going to need to know anything about like the linguistic aspect about this, about why this might get stemmed one way versus another way. But to actually answer the question of how is it getting stemmed, my guess about what it's doing is that all of the verbs are getting put into one location, stemmed together, and all of the nouns are getting stemmed together. And so slitted, past tense of the verb, will get combined with slit, is my guess. We could verify that by going into Postgres and actually inspecting the values of the TS vector to see how it gets stemmed. But I'm not going to do that because that'll just take us too far afield. A good question. Easy. The black boxes?
Yes. So the first part of it is saying like the first instance, right? Like what is it exactly saying?
The question is, what are these black boxes?
Like what are the numbers?
Yes, the question is, what is the numbers inside of the black boxes? The answer is that these numbers are the tuple IDs. So again, the tuple IDs, the very first number, the leftmost number is the page number, and the rightmost number is the index inside of the page. And that combination together is the tuple ID. This is the physical location of the row that this tuple represents on the hard drive. With a tuple ID, you can do a constant time lookup in the heap table in order to find the row that this corresponds to. In this case, the 02 right here tells us that where the location of the row that contains the word could is located. And so control F, find could. 02 is the physical location of this row on the hard drive. And so with that 02 number, with that tuple ID, we can do a constant time lookup to get this information. When we were looking at the pictures of the B trees, not the GIN index, but the B tree index, every B tree index has tuple IDs stored inside of the leaves, and every leaf node, every one of these individual white boxes inside of the B tree leaf, inside of the B tree itself, contains one of these tuple IDs, exactly one of those tuple IDs. They were not drawn because they contain exactly one each. In this case, though, the authors have decided to explicitly draw the tuple IDs here because they are potentially more than one in some locations. Like here, the posting list for sit contains 2, and the posting list for slit contains 9 different tuple IDs down here. In general, every index is going to contain somehow these tuple IDs. These are the things that we're gathering with our bitmap scan or our index scan in order to then search our heap table to find the information from these tuple IDs. The only scan method that does not use tuple IDs in any way is the index only scan, and the index only scan does not need these tuple IDs because all of the information for the whatever our query is contained inside of the index itself. Did that answer your question, Leisure? Yeah, good question. Any other questions so far? Let's see. So what's next down here, this last picture, is what's going to happen if we want to do a query, like a more complicated query. This first picture that we were looking at, this first picture up here describes the structure of the B tree, and we talked about how to do just a query where we're searching for an individual word. But what if we want to do something more complicated, like search for multiple words at once? And this picture down here is going to tell us how to search for multiple words at once. I'm going to come back to the notes here for a second. And if we look at this TS query section here, both of these queries down here that I have listed are searching for multiple words at once. This first query up here is searching for the word example and test, where the document that we're looking for must have exactly both of these, must have both example and test inside of the document. And this TS query down here is searching for example or test, where it either has example or it has test inside of it. And so this is the sort of motivation about what we're talking about next, is how do we sort of use this GIN index structure to solve queries that look like this. Coming over here, the two particular words that they're going to be looking for are this Manny word and this slitter word. And the first step is you individually search, find the posting list or posting tree for each of these two words individually. So for finding Manny, they do this going down left over here. Here's Manny. It contains only this individual tuple ID right here, this 0 and 2. And then for finding slitter, they come down over to the right. Here is the word slitter, and they find this posting list down here, or this posting tree down here. And the ability to combine both of these two things together, is why Postgres stores the information down here inside of a B tree structure. When we're stored inside of a B tree structure, it means that we can efficiently do like union and intersection operations on multiple B tree structures. And so we can take this result from Manny 02 and sort of find, does 02 exist in slitter? If it does exist in slitter, then, and we can do that using our standard B tree search operations, 02, it does exist in slitter down over here. And so we can answer the Manny and slitter query that way, by first finding the posting list or posting tree for one, and then doing the intersection of that posting list or posting tree with the other posting list or posting tree. So that is very high level how the these more complicated queries like the and the or are getting implemented. For your homework assignments, the only queries that you have are very simple queries that only have a single word, but for your final exam, I will expect you to understand the more complicated situation of the more complicated queries like this. Okay. I want to jump now down over here to the sort of the strengths and limitations of this indexes. So again, this gin index is being used for this at operator. The at operator is how we were combining the TS vector and the TS query to do our search. The at operator, again, you can read it as like contains. So the thing on the left over here contains the thing on the right. The TS vector contains this TS query. That's what this at operator, how to pronounce it. And the gin index, one of its uses is for speeding up this at operator. So far, we've only seen the full text search example. After we talk about the gin index and its strengths and limitations, we'll then go on to the JSONB. The limitations over here, though, the elements, lexemes is a synonym for elements that you'll see throughout the documentation. So any of those white boxes, any of those words are the lexemes or the elements that are stored in the tree. These white boxes up here, these are never deleted. And so this gin index can grow in size and not shrink. The tuple IDs down here, these black things, those will be deleted as necessary. So those parts can shrink. But this sort of root tree up here, that will never get smaller. It'll only grow in size. It's a little bit slow to modify this gin index because if you're modifying it, let's imagine you have to put in a new document. When you put in a new document, you're not going to match just one of these locations like you did in the B tree index. You're likely to match many of these locations. And so there's many pages that you're going to have to do an insert into. In slow mode of the gin index, it's actually going to modify that index every insertion. So in slow mode for the index add, it's going to modify potentially many pages every insertion, usually on the order of maybe like 50 to 100 pages every insertion. In fast mode, it's going to automatically, behind the scenes, batch up a lot of those insertions for you. And then when the vacuum operation is run, it's going to do those insertions in bulk. And the main limitation, though, of the gin index is that it does not store any sort of auxiliary information. So things like multi-column indexes, where we could have multiple pieces of information stored in one B tree index, that can't happen inside of a gin index. But the RUM index, which we'll talk about below in a second, that fixes this ability to store this auxiliary information. So if you're doing some sort of like document search, it's common to also want to search by the time the document was created or the page rank of a document. PageRank is sort of famously how Google first was able to do really good search results on the web. You can't add this sort of information into a gin index. You cannot add extra information into a gin index. Another useful piece of extra information is the position of the words inside of a document. So I'm going to come back up to our TS vector up here. The position, again, the TS vector stores both the position and the word itself, the lexeme and the position that lexeme occurred in. The gin index totally forgets about this position information. And so if your query requires two words to be right next to each other, the gin index is not useful for that. The RUM index solves most of these problems. And so we will, yes, the RUM index solves most of these problems. Before we talk about though, this last part 4 right here, one of the takeaways of these limitations up here is that the gin index does not support an index scan and does not support an index-only scan. It only supports bitmap scans. So if there's like one thing to understand about the gin index, it's this right here. This is the most important thing to understand about the gin index, that it does not support an index scan and it does not support an index-only scan. It only supports bitmap scans. Some of the implications of that are that it will not allow the limit operation to be sped up efficiently because the bitmap scan, again, has to scan through the entirety of the all of the results that get returned. It does not return results one at a time. So the limit operation cannot be sped up with the bitmap scan. It cannot be sped up with a GIN index. You need to be able to use an index scan or an index-only scan to speed up the limit operation. It also does not return results in sorted order because, again, the bitmap scan does not return results in sorted order. But the RUM index, again, by supporting these other scan methods, will fix this problem. This cluster operation is something that we haven't talked about in class. You're responsible for it for the final exam to understand what it does, and the GIN index does not support the cluster. We'll talk about the RUM index here next and how it fixes those problems, but any questions about the GIN index before we go into the RUM index? You go. Question is, which link talks about the cluster operation? Good question. So this cluster operation is described in several places in the required reading. It is going to be described a little bit in actually each of the links that I've given you so far about the indexes. It's mentioned inside of here. It talks about like why the GIN index is not clusterable inside of the GIN index page. It'll talk about in the RUM index page why the RUM index is clusterable. And the very first two links that are like the high-level overviews of the scan methods, it'll talk about what exactly clustering is. So it's sort of spread out in many places. But good question. Okay, the last index type that we'll talk about is the RUM index. And the RUM index was invented by the author, the Russian guy who wrote these blog posts. The GIN index, well, I want to talk about the naming of the RUM index for a second, both of these indexes. The GIN index, the documentation says that you should think about like GIN like a genie, not GIN like a drink. The Russian guy who wrote these posts said that as a Russian, he feels like everybody should be drinking gin all the time, but rum is even better than gin to drink, and so he called his index the RUM index. GIN properly stands for the Generalized Inverted Index. RUM has no like acronym for it other than the author liked to drink rum. Okay, so how does the RUM index fix our problems with the GIN index? I'm on the next documentation about the RUM index now, and there is a picture down here of the RUM index that we will go through. And this picture is based on the same series, or the same data set that we were looking at before with those same values, same rows being inserted, but now visualizing it as a RUM index instead of a GIN index. And the main difference here is that you can see that, so we still have these same white boxes up here, still the same stemming and stop word removal that goes on, because that happens at the level of the TS vector function, not at the level of the index. So all the white boxes will be the same no matter what type of index you're using. The black boxes down here contain the tuple ID information. This is, again, the physical location where the corresponding rows are located in the heap table. And every index is going to store these tuple IDs somewhere inside of them. And these gray boxes down here, this is the new thing about the GIN index, or sorry, the new thing about the RUM index that is different from the GIN index. And that is that the RUM index stores this extra information, stores this extra gray information inside of either the posting list or the posting tree, depending on which the index is using. What is this extra information? It is whatever you have decided to put inside of the table. So in this case, this extra information is just the location of the lexeme, the location of the word inside the document. But you could put whatever other additional information you wanted inside of here, and the RUM index will store that information for you. Because of this, storing this extra additional information, the RUM index allows an index-only scan and allows an index scan. So this allows you to return the information in sorted order according to whatever your meta information is up here without doing any extra additional like sorting operations. You get to actually speed up the limit clauses now because you are, again, returning things one at a time in an index-only scan or an index scan. And you'll have fewer page accesses when you do the index-only scan if everything is contained inside of the table itself. So the RUM index fixes vast majority of the problems speed-wise with the JSON index. And if people are using full-text search these days, they basically always use the RUM index instead of the JSON index. The main takeaway to know about the RUM index is that, again, because it's storing that extra meta information, all of those limitations about not being able to do bitmap scan or only being able to do bitmap scans and the downstream effects are solved, and the RUM index allows you to do every scan method. The downside of the RUM index is that it's going to be slower than the JSON index for inserting and updating because you're having more stuff that you are inserting. More space being used up than the JSON index because you're adding all of that meta information. And then a minor sort of downside is that it's not built into Postgres, and so you have to like compile it, install it separately as a separate extension. But that's a minor sort of thing. These are the main downsides up here. A very fast walkthrough of the RUM index. Any questions about that? Okay. Let's see. So that's basically it. One last sort of topic for us to cover. I skipped over this JSONB operations section right here. We're going to come back and talk about this next as our last thing today, and talk about how this will interact with your homework assignment. So your homework assignment over here, this Postgres indexes homework assignment. Again, I'm giving you this SQL.normalized batch, the list of queries over here, and all you have to do for this list of queries is write the indexes that will speed up these queries. Those indexes, though, will only work on the normalized data set because the denormalized data set is structured differently. The denormalized data set uses the views to recreate those same tables, and so it will be much slower using those views. In order to write, or in order to make the denormalized data set faster, what you'll have to do is you have to create your own new folder here that contains the 01 to 05, all those same problems, and you'll have to rewrite each of those queries in order that you in the denormalized form instead of the normalized form. In the denormalized form, these are the, I guess, the SQL operations that might be useful for you to explore the denormalized data sets. You're also welcome to take a look at the views to see how I was accessing things from the denormalized data sets. But this is going to be the most important of your operations that you'll want to use, this at operation, in order to access things from that data set. All of these functions up here, they are not directly related to speeding up a SQL query on the JSONB operation or the JSONB type. Only the at operation is something that can be sped up. So you'll have to figure out how can you use this @ operation to extract the appropriate information from the JSONB type. And then once you've done that, create the appropriate GIN index or RUM index to speed up that @ operation. I'm not going to go into detail on how to use these operations here. Again, my expectation is that you'll be able to use the references to figure out how to access the JSONB information and make your SQL queries the same between or give the same results between the denormalized and the normalized data sets. Are there any questions about that? Question, Beezer? About, sure. So the RUM index does support index-only scans, yes. The GIN index does not support index-only scans. The RUM index does support index-only scans. So here I say they can perform an index-only scan on the meta information. The meta information is the information that is being stored in these gray boxes over here. So if I was storing like I wanted to find what are the top 10 most common or the 10 most recent web pages that contain some word inside of them, then the meta information over here would also include the timestamp that those were created at. And so we could do an index-only scan on that with just looking at this meta information. Correct, yeah. Another example, a common example would be like if I want to do a count star, like count how many words, how many documents contain the word good inside of it. All that information is contained right here inside of the index. And so we don't have to access this tuple right here to see that there is just only one tuple inside of the that contains the word good. And so we could do an index-only scan for like count stars aggregates. Any other questions about anything? You go. Yeah, so the question is it slower to create a RUM index? And the answer is yes, it will be slower to create the RUM index. The main reason that it's slower is because there will be a lot more pages that have to be stored on disk because there's a lot more information being stored. And because there's more pages, there's just more things to write. The actual structure of the B tree itself is going to be the same because it's the same words up here that are being indexed. And the structures of these posting trees are going to be the same as well because it's the same tuples that are being associated with each individual word or lexeme. And so the structure of the tree is going to be the same. So it's not slower because of that. It's just slower because it has to store this extra meta information as well. So it's not a lot slower, maybe just like asymptotic complexity-wise, same asymptotic complexities, maybe like a factor of 1.5 or 2 times slower, something like that. Any other questions about anything we covered today? Okay, then I think we'll just end class a little bit early, and next time in class again, we will go over the format of the final exam, what to expect, how to prepare, and do a lot of practice problems related to that. If you do have any questions about anything, homeworks, or the material from today, happy to stick around and get those answered. Otherwise, I will see you all on Thursday.